and welcome everybody to another complex webinar. I really encourage you all to fill out the survey. We have a fairly small group today, about 25 external people, so your chances are pretty good, and we really rely on your feedback to continue to improve our program. So let me go ahead and share my slides. Okay, and Cindy, can you just confirm that you are seeing my slides and they are advancing?
Yes, I do.
Okay, great, thank you. Okay, so today I'm going to be talking about Linux tools for text processing. There is a GitHub repo that accompanies this talk, SDSC Complex Linux Text Tools. You'll kind of hard to do this interactively on a webinar, but I suggest that you visit the GitHub site after the talk and work through the examples. And if you want access to PDFs of the slide, you can find those in the bit.ly/complex. Okay, so a little bit about complex if you haven't been to one of these webinars before. So complex stands for comprehensive learning for end users to effectively utilize cyber infrastructure. So I know that's a mouthful. We came up with the acronym first and then worked backwards to make it fit to a name. But this is a new program that we have at SDSC for training that covers the non-programming skills that you need to effectively use supercomputers. So topics include parallel computing concepts, Linux tools, bash scripting, security, batch computing, how to get help, data management, and interactive computing. And we always like to acknowledge that this work is supported through a grant from the National Science Foundation. So table of contents, we're going to start off with an introduction. Then we're going to look at a number of different tools that I have listed here. We're going to be going kind of in order of the difficulty. Head, tail, paste, NL, and so on are pretty straightforward. Sed and awk are considerably more complicated, but we'll just highlight a few of the key features. We'll look at some case studies, and we'll wrap up by talking just a little bit about how you could use LLMs to help you use these tools. So I'd like to say that this session is intended for anyone who needs to post-process text files to extract runtimes, results, or information about the hardware used for the calculation. The skills that we're teaching here are also going to be useful when constructing workflows, preparing high-throughput computing workloads, or pre-processing data to get into the correct format. So I can't emphasize enough how important it is to be able to manage these sorts of tasks efficiently. You know, if you're doing deep learning or data science in general, you'll find that much of your effort is spent on what we call data munging, just taking data, get into the right format so that you can begin your training or your analysis. So we're going to be providing you with some of the tools and programming languages that you could use to make all of these tasks much easier. So the Linux environment provides a wide range of tools for sorting, splitting, manipulating files, along with tools for extracting content based on location or value. So I think I mentioned this already, we're going to be looking at split, head, tail, sort, shuff, NL, awk, sed, grep, and paste. So a lot of these tools have many, many options. We are not going to go through all of them. I'm happy to take questions throughout the talk. But if you get too deep into the specifics of options for any of the tools, even I'd have to go back and look these up. So today we're really going to be just looking at the basics. And if you like to, if you feel that one of these tools will be useful for you, you always have the option of diving a little bit deeper. So you might be thinking, can't I just do this all by hand? Do I really need to learn yet another tool or tools? And you know, I could understand why you might ask these questions, because you know you might have a workflow, a process that's already working for you. Maybe you are doing some of these things by hand, but I would say that there are three drawbacks. First of all, it could be time consuming. So you're going to spend a little bit of time learning how to use these tools, But once you make that investment, you're going to find that there should be a big payoff. A lot of these tasks, they could be tedious. And I would say the third point is the biggest one, and that's when you're doing text manipulation by hand, it could be error prone. And this is especially true if you're doing something many, many times, say extracting a value from potentially thousands of files generated during a parameter sweep calculation. So what we're going to try to do is automate the process. Now, sometimes you're going to run into data processing tasks that require you to develop relatively complex parsers that might be beyond the ability of non-programmers to write, but often these simple Linux utilities are going to be sufficient for your needs. So just a brief digression on Linux philosophy. And I think this is worth reading. It's a report from Bell Labs back in 1978. And the authors laid out what they considered to be their Unix philosophy, which I feel is still relevant today. So I won't go through all of the text here. It is worth reading, but let me just highlight, I think, a few of the key points. So first of all, in the Unix and now Linux world, they had an emphasis on making each program do one thing well. So for example, sort only sorts the contents of a file. Head only lists the first few lines. NL only adds line numbers to output. So they didn't try to come up with general purpose tools that do many, many things. Instead, they created what I'm going to call smaller tools that were very focused to do one thing and to do it well. Another key piece of philosophy was that you should expect the output of every program to become the input to another as yet unknown program. So they didn't clutter the output with extraneous information. They avoided strict column format or binary inputs. They didn't insist on interactive input. So this is going to make it very easy for you to take the output of one tool and pipe it in as the input of another. And then use tools and preference to unskilled help to help lighten a programming task. So see my earlier comments about avoiding tedious, time-consuming, and error-prone tasks. You might be tempted, say if you're faculty and you have students who are working with you, to say, hey, this is a tedious task, I'll just hand it off to a student. But I would say, maybe you could hand these things off to students, but have them develop tools or combination of tools to do these tasks. Your students are going to be moving on, and you want to make sure that you have a robust solution in place after they're gone. We have a number of hands-on examples in the accompanying GitHub repo. So you don't really learn these tools until you start experimenting with them. So what I'm going to suggest is, try deliberately introducing errors, leave out quotes, commas, or semicolons, see what happens. Try extending the examples to introduce new features. See if you could chain the tools together to create more complex workflows. And best of all, apply the tools to your own use case. So if you're doing data science or computational chemistry or neuroscience, see if there are places where you can apply these to your own research. And I think it's going to help you learn how to use these much better than if you're just working on, say, abstract examples. So with that, we're going to look at our first tool. We're going to start at the very shallow end of the pool with head and tail. And what these tools do is output the first and last part of a file. Very, very easy to use by default, and many of these tools have sensible, reasonable defaults. By default, head will give you the first 10 lines in a file. So I had this file.txt, that contained 20 lines, where the content is line 1, line 2, and so on. Head shows me those first 10 lines. Tail shows me the last 10. As you would expect, the user can override the default and specify the number of output lines. So here I use the option -n7 to list the first 7 lines in the file. And then with tail, likewise, I do -n7 to list the last 7 files. You can also specify that all but the last certain number of lines be output. So in this case, I use a head dash n, in this case, a negative number. And also with tail, I could use a positive number. So for example, if I did a head dash n dash minus 15 file.txt, I will see everything except the last 15 lines. And if I did a tail dash n plus 16, I would see everything except the first 16 lines. So pretty straightforward, much more convenient than, say, writing the entire content of a file to your terminal output, or say opening it with an editor. So moving up the food chain, we're going to look at a slightly more complex tool, but really, really convenient. This is one that I'll admit I had only discovered fairly recently, maybe about 5 years ago, even though I had been working in a Linux environment for decades. So every once in a while, you'll need to combine the contents of 2 or more files, and you'll want to do it line by line. And I think the way a lot of us do this is we'll write the output say to our terminal. We'll mouse over that text, paste it into a spreadsheet. Do the same thing with the other text, paste that into a spreadsheet, and so on. But paste allows you to do this very, very easily just by specifying the names of the files. So let's say we have 2 files, fruits.txt, and it lists apple, banana, grape, and then we have another file, colors.txt, contains red, yellow, purple. If I just simply do paste fruits.txt, color.txt, then I will write the standard output, a new output that merges the lines from those 2 files together. And you can also do this with multiple files. And you can also use the same file multiple times. So we could have done paste fruits.txt, colors.txt, fruits.txt. Now, sometimes you'll want to specify a delimiter, and as you might expect, paste has an option for doing this. So instead of, say, having the default output, which was data separated by a single space, we can instead specify an arbitrary delimiter. Very often that's going to be a comma. So here I did a paste -d and then in quotes comma, fruits.txt, color.txt, and now I get CSV output, which I could then read into a spreadsheet. Okay, going just a little more complex, we're going to look at the NL function. And this is one that I also discovered fairly recently. NL command adds line numbers to a file. So I'm going to say this is not an essential command, since the same task could be done using other tools, but I find it to be extremely convenient. So let's go back to my fruits.txt again. If I do NL fruits.txt, and this is the default, then my output is going to be 1 apple, 2 banana, 3 grape, and so on. Like all of the other Linux commands, there are going to be multiple options. A really convenient one is to left justify the line numbers. So here I do a -n, and then ln is the option for left numbering. And now I have what might be a more convenient output. 1 tab banana, 1 tab apple, 2 tab banana, 3 tab grape. Now, I said that there are other ways you could have done this, and I experimented with a few. Two options down here. I could use the seq command, seq, to generate a sequence of numbers, and I pass as an argument the output from wc-l on fruits.txt. So basically, it's looking at the number of lines in that file. I could then write that write that sequence of numbers to new file, and then I can use a paste. You can see that is really a much more roundabout way of doing this. Using NL is much simpler. We could have also done this using the awk command, which I'll be getting to a little bit later. All right, so now we're going to get just a little more complex. So we're going to start looking at sort. So you're probably all familiar with doing sorts in spreadsheets, but you could also do this from the Linux command line using the sort function. So without arguments, again, you get a very reasonable default. Your sort is going to be done. Your sort is going to be done by lexicographical order. So be aware that the handling of upper and lowercase letters is going to depend on your environment variables. So if I do, let's take a look at this file. I'm going to call it unsorted1.txt. And we see we have names of fruits, some in uppercase, some in lowercase. So we have banana with an uppercase B, apple with a lowercase a, grape with an uppercase G, and so on. And you'll see that some of the lines are repeated. So we have banana up near the top, and then close to the bottom, apple, grape, and so on are repeated. So if I do a sort with no other arguments, I'm going to get this lexicographical sort: apple, banana, grape, orange, peach, pear. Notice though that apple, lowercase apple, does appear before banana, and so on. That this is a sorting that I think you would normally want to do. But keep in mind that there is an environment variable, lc_all. We could set it to C, and then if we do a sorting, we will get the ASCII order sorting, where all of the uppercase letters appear lexicographically before the lowercase letters. So now you see we have banana and grape, which are uppercase, followed by the lowercase words, apple, orange, peach, and pear. Now, if that was all that sort could do, the utility would be a little limited, but there's much else that we could do with sort. And to me, the most convenient one is that you can choose the field that you want to sort on. So if you're familiar with using Excel spreadsheets, I'm sure you've done this many times, where you might sort by the first column, the second column, or so on. You can do the same thing with the Linux sort. And the way we control this is with the K option. We can also choose to sort by numeric value using the -n option. So let's go back to another unsorted file. We're going to call this one unsorted2.txt. And we can see that each line is a fruit followed by a number followed by some type of fast food, taco, pizza, hot dog, and so on. So if I just did a sort on this file, I would be sorting, treating each line of that file as a single string. So the first line would be apple, 6 pizza, the second line would be banana, 17 taco, and so on. But let's say that I wanted to sort on that last field. What I could do then is specify, instead of using the default, -K3, and here I'm saying that I want to sort on that third column or on that third field. So now we could see that we're sorted by that last field. So the lines are grape 23 hot dog, pizza, popcorn, pretzel, and taco. Let's say I wanted to sort on the second field. I could do a -K2. And you'll notice that the output is maybe not what I was expecting. So here I have, in that second column, 12, 17, 23, 35, 6. And if you look at that, that is definitely not a numeric sorting. What happened is we applied a lexical sorting. So in the ASCII sequence of characters, 1 comes before 2, which comes before 3, and so on. So now we got 12, 17, 23, 35, 6. If we wanted to do the sorting numerically on that field, here we could say -K2. So we're going to sort on the second field, -N. So the sort on that second field is done numerically. And you can get a much, so just highlighting here that if we don't specify any options, we get lexicographic ordering. But if we use -n, we will get the expected numeric ordering. Sort can be restricted to listing unique values by specifying the -u option. So sometimes this is really handy if you just want to find out what are all the unique values in my file. So again, going back to our previous example, the unsorted one.txt, we see again banana, apple, grape, pear, somewhat random order. If I sort this, we get apple followed by banana, grape, orange, and so on. And note though that we do have repetition. The line apple appears twice, banana appears twice, grape appears twice. If we did a -u, this is going to give us just the unique values. So now it's restricted to apple, banana, grape, orange, peach, pear, sorted, but also reduced to the unique occurrences of each line. And then finally, we can do a multi-column sort. So we can use the K option multiple times. And we can also restrict the sort to only data in this column. So the syntax is a little more complicated. We're also throwing in there the R option to do a reverse sort, and N, as we saw earlier, for numeric sorts. So let's look at another example. We're going to call this file unsorted3.txt. And in each line, we have a fruit, a color, and a country. So this could be, say a list of produce, listing the type of fruit, say the color and the country of origin. So we could sort this multiple ways. So let's say that first we wanted to sort by country of origin. Then within that sort, subsort by the fruit, followed by the color. So here we can see that the first 4 lines are all Canada. The next 4 lines are Mexico, and the next 4 lines are USA. And then within the group of fruits coming from Canada, we can see that we have all of the apples listed, followed by all of the bananas. And then within each of those fruits, sorting by the colors. So apple green, Canada, apple red, Canada, and so on. We could have also done reverse sorting here. So in this case, we wanted to do a reverse sort first on the color. So we have a -K2R, 2. This means that we are going to get all of the reds, followed by all of the greens. Then we're doing a sort on the first field, apple, banana, and so on, and then finally by the third field. And finally, one more option that you should be aware of for sort, and that is to randomly shuffle the data. But I'm going to tell you to use the shuff command instead of sort, because there's a little, unexpected quirk with sort. So let's say that you have a data file that you want to randomly sort the data. This might come in handy if you're doing, say, training of an image classifier, where your file might be a list of all of the images, and let's say they're labeled cat1, cat2, cat3, cat4, and so on, dog1, dog2, dog3, horse1, horse2, horse3. You would like to randomize that data so that you could split it into groups, say, of your training, testing, and validation data. You don't want to take just the first 80% of the lines, because then you might have all of the cats, all of the dogs, and none of the horses, and so on. So what you could do is you can shuffle that output. Now, sort has a -R option, which will let you do that random sorting. But the problem is that it will take all of the instances of matching lines and it will group them together. So if I look at my file again, abc.txt, 3 lines that contain A, 3 lines that contain B, and 3 that contain C. If I do a sort dash R, and you're going to get a different result each time, you'll see that we get all of the B's followed by all of the C's followed by all of the A's. A better way to do this is to use the shuff command. So in this case, you really do get a random ordering. And if we look at the output, we'll see that the 3 B's occur at random locations throughout the output. Same thing for the A's and the C's. And finally, if you want a random permutation of integers, and this is a good example of chaining these Linux commands together, I could use the seq, S-E-Q command, feed an integer input 9, so it's going to generate a list of 9 integers, and pipe that into shuff. So really, really easy ways to take your data and to randomize it. So with that, I'm going to take a quick break. Cindy, do we have any questions yet?
No, we do not.
Okay, great. So I'm going to move on to split. Our commands are going to start getting a little more complicated. So the split command will take a file and it will split it into pieces. So split will, by default, break a file into chunks of 1,000 lines, and it will use a naming convention where the files are called XAA, XAB, XAC, and so on. So let's say I have a file, we call it genome.fasta, and I split it into chunks. Let's say it's a very, very large file. I don't want to process it all at one time, or I want to assign the processing of the data to different programs. So I do split genome.fasta, and I'm going to do a wc-l, see how many lines there are in each of the files. So we started off with genome.fasta. It had 9,991 lines, and then the chunks that were generated, XAA, XAB, XAC, you'll see that they all contain 1,000 lines. And then finally we get down to XAJ, and it contains 991 lines. So what split will do is it will try its best to break it into chunks of the same size. But if the file cannot be divided evenly, the last output file is going to get whatever is left. So if, for example, we had genome.fasta containing 10,001 lines, we would end up with 10 files that each contain 1,000 lines, one file that contains 1 line. We could also specify what the chunk size should be and what the naming convention should be. So XAA, XAB, and so on, the names aren't terribly intuitive, but let's say I split my file. Here I'm introducing two new options, -L 2000, say that I want chunks of 2,000 lines, and I want to use genome underscore for the naming prefix, and now I get genome underscore AB, genome underscore AC, and so on. Those first 3 files each contain 2,000 lines, and then the 4th file, again, has whatever's left over, 1,991 lines. Okay, now for files that have a well-defined structure, such as FASTA files used for genomic data, the default record separator, a new line character, may lead to undesired behavior. In this case, let's say we wanted to keep the annotation and the sequence together. So if you're coming from a bioinformatics background, these sorts of file formats will look familiar. We see here that my first chunk, genome underscore AA, starts off as I expect. The next chunk, though, genome underscore AB, it looks like I started somewhere in the middle of one of the FASTA records, and so on and so on. So what I can do is I could specify a different record separator. So here we're introducing a new option, the -T option, which controls how the file is split. Now there's one wrinkle here, and that is that the delimiter is consumed by the split operation, which means that it is not printed out. So if we look at the output, it's much, much closer to where we want it to be. Each of these files, it starts with an annotation line, so we're keeping the annotation and the sequence all together, But you'll notice that starting with genome AB, and so on, that we lost that initial greater than sign. And I'll show an example a little bit later when we tie this together with other tools of how we could fix that. Okay, moving on to grep. This is a tool that I think you're going to be using all the time. At its simplest, grep returns all the lines in a file containing the search string. Remember that upper and lowercase letters are different characters, so you'll need to use the -i flag if you want your matches to be case insensitive. So we're going to go back to, to another example. This one we're going to call it file1.txt. And each line just contains names of 3 different fruits: apple, banana, pear, cherry, banana, peach, and so on. And notice that I do have, some of the names appear in both in upper and lowercase. For example, we have lowercase banana, uppercase banana. So if I do a grep small b banana file1.txt, I'm going to list out to standard output all of those lines that contain banana. So we get apple, banana with lowercase b. So we get the apple, banana, pear, cherry, banana, peach. Similarly, if I do grep banana with an uppercase b, I get apple, banana, pear, cherry, banana, peach. In both cases, the banana is uppercase b. And if I do -i, then I will get both options. I'll get both banana with the lowercase b and the uppercase b. So this is probably one of the biggest, I'm going to say, stumbling blocks with using grep, and that's not being aware of the that the searches are case insensitive. So sometimes you might be using grep looking for lines that contain certain words that you have in mind, and you're not getting the full output they expect. So be sure to use the -i flag if you want those matches to be case insensitive. Okay, grep, if you look at the man page, there are a lot of options. I'm not going to go through all of them. A couple that I find really, really useful, though, are seeing the context of the matches. So I have a capital B and a capital A option, which says that I want to see, in the case of --b, I want to see a certain number of lines before each match. So let's say I was doing a search for kumquat, but I don't just want those lines, I want the lines that appear before it. So here I did grep-b, 3 kumquat. I'll see 3 lines followed by pear, kumquat, grape. Similarly, I could look at lines that occur after my match. So here I did grep-a2. Think of the B as being before, A as being after, and now I get the lines that match kumquat along with the following 2 lines. And you could combine these. So I could have done, for example, grep-a1, -b1, kumquat, and I would see the lines matching kumquat, the line before and the line after. And this will occur for every match in the file. Couple other helpful options are doing an inverted search. So let's look at our file again. We're going to do a grep lime, and we're going to see all of the and we're doing this across multiple files, file1.txt and file2.txt, and we're seeing output of all the lines that contain the word lime. But let's say I wanted to flip that around and I just wanted to get all the lines that do not contain the match. I could have done a grep-v to invert that. So now I get output of all the lines that do not contain lime. So again, a lot of options in here. Just play around with them. Use the ones that you need. So we could also use grep to look not just for the matching lines, but for the number of matches and the files that contain a match. So again, let's take a look at the lines from these 2 files, file1.txt and file2.txt, that contain lime. We see that there are 2 lines in file 1, 3 lines in file 2. If I'm trying to get a line count, this case is simple enough that I could do it by eye. I could say, oh, I see that I have 2 lines that are labeled file1, 2 lines that are labeled file2. But if I use the -C option for a count, I get the number of matches. So in this case, I'll see file1 does have 2 matches, file2 has 3 matches. I could also use -L to list all the files that contain a match, or -L to see all of the files that do not contain the match. And finally, going a little bit deeper, we're just beginning to touch on a more complex topic called regular expressions. This is a way to define strings of characters. But grep can recognize more complex patterns using character classes, anchors, and even these regular expressions. So again, let's look at all of the lines in file1 that contain pair. You see that we get four lines of output. And notice that in 2 of these lines, pair appears at the end, and in 2 of them, pair appears at the beginning. Now let's say I wanted to find just those lines that started with pair. So not all of the lines that contain pair, but only those that begin with pair. I could now specify in single quotes, caret pair. Caret is what we call an anchor for specifying the beginning of a line. So now we'll find all of those matches of pair that appear at the beginning. We also have an anchor, a $, that we can use at the end of our search. So here we're looking for lines that end with pair. So here grep, and then single quotes, pair $. Oh, let me go back. All right, and I'm going to move on now to 2 much more complex tools. So these tools sort of violate the Unix philosophy guidelines that we covered at the beginning of this session. But I'm going to say it's okay because things like grep and shuff and sort and so on, these are simple tools that are meant just to do one thing. Sed and awk are actually full programming languages. Now these are extremely powerful tools that operate on streams of data. We could easily spend days exploring sed, and entire books have been written about it. But we're just going to look at some simple examples demonstrating 2 commonly used features. If you're really interested, you could follow these links. I had worked through the sed and awk tutorials and manuals, and each of them took me about 2 to 3 weeks to work through. So it's a really, really deep dive. I'm going to guess that most of you probably don't want to invest that much time. I figured since I'm doing this for training, I'd want to go a little bit deeper, but it is a lot of work. I'm just going to focus though on a few things that I think you're going to find particularly useful. So most of the time when you use sed, you're going to use it to do some sort of replacement on every line of a file. So while some of these operations can easily be done using a global replace in a traditional editor like VI or Emacs, sed has the advantage that it could be scripted. It means that you don't need to use your editor, open up each file, execute a series of commands. In addition, since it works on a stream of data, the entire file does not need to fit into memory. So imagine that I'm working with a very large text file that is 10 gigabytes in size. If I try to open that with Emacs, it's not going to work. The file is going to be too large. If you're working on login node, you're not going to have enough memory. Even if you're working on one of the compute nodes that has more memory, eventually you may get to the point where the entire file doesn't fit into your editor, and it can take a long time to load. So using sed, given that it's a stream editor, that it's streaming through that data 1 line at a time, we're really not limited by the size of the file. That file does not need to fit into memory. So what you're often going to do is sed, and then in single quotes s, which means substitute, slash the thing that you want to replace, slash the thing you want to replace it with. And there are 2 ways to use this. Without any other options, we're just going to do the first occurrence on each line. If we add the -G before that closing quote, it's going to do a global replace on each line. So let's look again at the file1.txt, and let's say that we want to replace each instance, or sorry, replace the first instance of pair in each of those lines with four capital X's. So as we go through here, we'll see in the first line, pair was the first field, replaced with 4 X's. In the second line, pair was the last field, again replaced with 4 X's. When we get into the next few lines, each of those lines have multiple occurrences of pair. But notice that in each case, it was only the first occurrence that was replaced. So we had in that third line, pair, apple, pear, grape. This becomes XXXX, apple, pear, grape, and so on. If we wanted to replace all of the instances, we could add that -G option. And now you can see that in each line, we did a global replace of pair. We can also specify that we want to restrict to instances at the start of a line. So here I'm going to use the anchor that we saw with grep. I'm going to replace, instead of pair, it's going to be caret pair. So now we're going to replace pair with XXXX only if it appears at the very beginning of the line. And we could also use the $anchor so that we only do the replacement if the string occurs at the end of the line. Sed also has ways for mechanisms for printing out specific lines. The syntax is a little dense, but if you wanted to print out, say, just the 5th line of the file, lines 3 through 5, or every other third line starting at line 2, you could follow the syntax that we have here. But I'm going to say 99% of the time, this is probably what you're going to be doing. You're going to be doing a replacement of text within your file. Just one thing that I want to point out, though, is that said, how would I put it? That you can run into a problem if you're trying to do this in place. So let's say that I want to replace pair with XXXX in file3.txt, and I then redirect that output into file3.txt. What's going to be happening is line by line, we're going to be applying this transformation. But then when we're done, we're going to end up with nothing. We concatenate the output. That's because we're trying to write to the file as we're streaming through it. If we want to do an in-place replacement, we can specify -I option. But keep in mind that if we use -I, it's now going to be required that the file is read into memory. And now I'm going to cover awk very quickly. This is another very, very powerful tool. You could easily spend a couple of weeks working through awk tutorials, but I will limit us to what I think is the most common use case. So we'll start off. Awk is a general purpose programming language for manipulating text, and an awk program consists of one or more rules containing an option and/or an action. So we'll have a pattern, and then in curly braces, an action. Most of the time, you're going to use awk one-liners, something that could be executed from the command line. We would say awk. We would then have our pattern and action in single quotes, followed by a list of files. And we can have multiple actions separated by semicolons. And there are also special actions that are executed once at the start and at the end of an execution. I'll show those in the next few slides. So the most common use of awk is to print selected fields from each line of a file. Awk, like said, processes the file one line at a time. It will split it into fields referenced by positions $1, $2, and so on. And the last field can always be accessed using the special variable nf as $nf. So let's look at a file here, people.txt. I just put together a random list of names, pets, I guess favorite food, favorite fruit, and favorite color. If I wanted to print out the first, the third, and the last field in each of those lines, I could do awk, and then in single quotes and in braces, print $1, $3, $nf. So now we get Bob Meatloaf blue, Cindy pizza purple, and so on. So that's probably going to be the most common use of awk, just printing out particular fields from your output. The nf variable is particularly useful if you don't know the number if you don't know the number of fields in each line, or if you're working what we call ragged data, where each line has a different field count. So if I'm looking at this ragged data and I just want to get the last field in each record, I could do a print $nf and I just get that very last field. awk can also take a search pattern and include other text in the output. So let's say I want to get a little bit fancier. Instead of just printing out field 1 and field 2, I'm going to add some text in there. Here I said in double quotes, favorite food is. So now we have Bob, favorite food is meatloaf, Cindy, favorite food is pizza, and so on. I could also use a pattern here. So notice before the action, I now have a very simple regular expression, just a single string pizza. So now I'm limiting awk to operating on those lines that contain the word pizza. So you could think of this as a combination of grep and the simpler use of awk. By default, awk uses white space as the delimiter, but this can be changed using the capital F option. And this is going to be really helpful when working with comma-separated value, or CSV files. So if you look at the file states.txt, and all of these examples are in the GitHub repo, you'll notice that we have some embedded spaces. So if you go down to that last line, you'll see in Pennsylvania, the state bird is the ruffed grouse, ruffed space grouse. The state tree is the mountain laurel, or state plant. So if I do a if I don't specify delimiter, I'm just going to end up splitting on white space, and the results are going to be very much not what I want. So here I'm going to use the -f option, specify the delimiter to be a single quote, and then print $1, state bird is $3, and operate on the states.txt file. And now we can see that we get the input that we expect. Finally, awk has some basic math capabilities. So in addition to addition, subtraction, multiplication, and so on, it can do square roots, logarithms, exponentiation, trig functions, and random numbers. So let's say I'm looking at a file, numbers.txt, that contains numeric fields. Here I could calculate, say, the sum of those first two fields. I'm going to say sum is equal to $1 plus $2. Product is equal to $1 times $2. Have all of these separated by semicolons, and then followed by the print statement. Print $1, $2, sum prod. This is really, really convenient. It allows you to work directly with the text files and say not have to either write a program or import them into a spreadsheet to do these operations. And just a few more examples showing how you could use sines, logarithms, cosines, and square roots. We can get even more complicated. By default, awk applies operations to each line, but begin and end allow you to execute additional code just once at the start or the end of file processing. This is really handy if you want to accumulate values or if you want to provide headers. So in this example, and we're getting a little short on time, I won't go through the whole thing, but we could see that we start off with awk, and then, in our action, begin, and then in curly braces, we define pi, and we print out a header, x, y, sine x, cosine y. Then we do some math operations. We print out the results using C-style formatting. And we can also calculate sums, averages, and other quantities over columns of numbers. So here I am, in the beginning of my awk command, I am accumulating a sum over the first field, a sum over the second field, and at the very end, I print out those sums divided by the numbers of records. So you can see what we've done here is in our simple file that contained 1.1, 2.2, 3.3, 4.4, and so on, I now have a sum of that first column and a sum of the second column. So I know we're going through everything with awk and sed very quickly. This is more last few examples, just to demonstrate some of the things that you could do. And I'm going to say if you're interested in these sorts of use cases, be sure to grab that GitHub repo and experiment. So when you do grab the repo, you could either download it and run it locally, or I also have a binder option in there so that you can run this on the cloud. So I'm just going to go very, very briefly through some case studies. The examples we've done so far have been a little contrived, things like lists of fruits and favorite foods and just a few columns of numbers. But I'll show you a few real life examples where I've used multiple tools together in my own work. So first case study is parsing the output from high performance LinPack. So whenever we deploy a new supercomputer, we run thousands of HPL jobs to ensure that all the nodes are functioning correctly and delivering the expected performance. So what this requires is for each output file is that I extract the name of the node that I was running on, the runtime, and the completion code, whether or not we got the correct result. So this is just a little bit of output from HPL. Not going to go into all the details. I'm not even showing the entire file, but I've highlighted the fields that I want to get. So this VGR 10-01, that was the name of a node on our Voyager supercomputer, appears right at the top of the file. We have a line down here where we have a runtime. This tells us essentially what the performance of that node is. And then finally down here, we have a line where the last field is passed or failed. Lets us know what the status of that run was. So I was able to combine tools together, start off with echo to print a header line. I loop over all of the files that have name output.hpl star. I will then extract the first line of a file. I'm using grep, multiple greps, capturing the output and pasting it all together. Again, don't have time to go through the whole thing, but if you're interested, take this example, see if you could apply it to your own work. So when I do this, I will then go through all of the files that begin with output.hpl star, and now I get a output labeled by node time, pass or fail, and all of the data that I need. So again, much easier than opening up each of those files individually and cutting and pasting results. Another example, this was benchmarking of output from the BERT natural language processing software. Again, we wanted node number. There was some other information that we didn't want to get, say timestamps, number of sentences per second that we could process, and the percent of the time that we got the correct output. And again, this is going to look a lot like the example that we saw previously for HPL, where I'm using a combination of head and grep and so on to, and awk to capture all of the data that I need and write it to a space-limited file. And I'm going to skip over the last example. This is a little more specialized for those of you who are doing bioinformatics. But if you are a bioinformatician and you're running into the issue with splitting these FASTA files, you could just probably use this example as is. So we are just about at the top of the hour. I'm going to touch on one last topic, and that is using LLMs. So I'm going to guess that pretty much everybody here has at least played around with ChatGPT. If you do any program, you know that it's very helpful for helping you to write code. So LLMs can definitely help here, but it's still valuable to know a bit about these tools and their capabilities. So for example, if you didn't know that awk existed and what it could do, you might not even know how to ask the right question. But let's say, I haven't used awk for a while. I kind of know what I want, what I want to do, but I'm not familiar with the syntax. I could have gone to ChatGPT, and this was the older example. This is probably ChatGPT 3. Um, Now GPT 3.5 is available free to everyone, and 4 should be free pretty soon. Um, so I said, can you give me an awk one-liner to print the second and fourth lines from a file? And it gave me this awk one-liner. And then I followed up. I said, now can you add the condition that this is only done for lines where the second field is greater than the fourth field? So it generated another awk one-liner for me that this time with the pattern $2 greater than $4. And then I was also able to do this for a sort command. Said, can you give me a Linux command to sort a file by the second field numerically and then by the first field in reverse alphabetical order? And it was able to do that for me. So I'm going to wrap up. Just say Linux gives you a powerful set of tools for doing text manipulation. They can improve your productivity and reduce the likelihood of making errors. Don't be discouraged if you didn't understand everything. We covered a lot of material in a pretty short time. We started off very easy with things like head and tail and paste. And then by the end, it was probably like a blur as we were going through awk and sed. Today wasn't so much to teach you everything you need to know about awk and sed, but just to present the basic capabilities so that you have a starting point. We've barely scratched the surface, especially for the more complex tools. So while you can go much deeper, we probably covered most of what you're going to need to know. And LLMs can definitely help, especially for the more complex tools. But I still recommend that you at least know the basics so that you can formulate meaningful prompts. And with that, I am going to wrap up, and I am happy to take any questions.